Thank you. You almost pronounced my name correctly. Just kidding. So, good evening. How many of you here, just trying to make sure, does this work? Apparently only goes forward, so I'm a bit afraid to press it too hard because then I cannot go back. Let's try it again. Anybody? I can describe my slides, but it's not going to be that interesting for you guys. OK, finally, OK. So how many of you here have heard of Elasticsearch? All right, that's half of the people. There are these lights burning my eyes, so it's kind of hard to see in the audience. Elasticsearch, in a nutshell, is a scalable, real-time search and analytics engine. It's open source. You can find it on GitHub. You can download it, use it, fork it. You can do whatever you want with it. Now, I could open up the buzzword dictionary and tell you that it's multi-tenancy, it's schema-free, document-oriented, cloud-friendly, but I'm not going to do that. And rather talk about some use cases, about some organizations that are using Elasticsearch to manage pretty much the entire data set. Wikimedia is one of those organizations. Throughout all their websites, they actually use Elasticsearch. So whenever you're doing a query, whenever you're looking for some type of information or answer on Wikipedia, that's actually Elasticsearch. You're one of the hundreds of thousands of users at a certain point is looking for information in Wikipedia massive data store. Now, we're all developers here, so I assume most of you are familiar to some degree with GitHub. You're potentially forking code, checking out, or maybe doing commits. And every time you do that, you would keep adding to GitHub enormous repository. There was a blog post, I think, a couple of years ago, where they were explaining how they're using Elasticsearch and giving some impressive numbers. 130 billion lines of code, I think, several terabytes, hundreds of terabytes of data. So I would imagine by now, in 2 years or 3 years, they probably passed the 1 trillion threshold. So I have to open up the buzzword dictionary again and say, that's pretty web scale. Now, GitHub provides a nice integration, at least for developers, to what Elasticsearch is. So when you open up GitHub and type in anything such as Elasticsearch, you're doing a search throughout, an unstructured search throughout the entire data set, be it repository, issues, gists, comments, everything that you put in, it's indexed in real time and made available so you can search it right after. Right? And it doesn't matter how many users are doing that, it simply works. And as you have a lot of data, you're going to get a lot of information out, so you can sort it, you can decide its relevancy, you can paginate through it, right? Because there's a lot of data. You're not going to find only one answer, you're going to find multiple answers. It depends to you and your criteria how good that answer is going to be. And you can also do some interesting things. One of them is enrichment. Things like highlighting. Where does this particular term occurs? The offset, the position, is it in the title, in the description, is it a comment? I can see the context, and that's quite powerful. You can have suggestions. So as you type in, you can find the usual answers and provide some type of feedback, so you can actually narrow down the search as you type it. And also do interesting other things like structure search. So again, I assume most of you here are familiar with this interface. But as I said, typically you would start in and type a query. You don't know exactly what you're looking at. You're basically looking through all the data assets in GitHub. And as the data comes in, you're seeing being broken down. That's basically some type of analysis. So you can see that, OK, the results that are coming in are repositories, basically code, issues, users. So the data is being bucketed, is being broken down per some common criteria. In each bucket, in this particular case, the repositories are broken down even further in smaller buckets, such as a language. So I can see, OK, I'm looking at repositories, and some of them are in Java, some of them in JavaScript. So literally what you're doing, as the data comes in, you start to structure it so you can actually better get context. And what you're doing by that is going from an unstructured search to a structured search. This is what we call, and this is an example of Elasticsearch analytics capabilities, where you move from search as your typical full text search, which is more people think about it, to actually a generic global type of searching. And in many regards, we see Elasticsearch as an exploratory tool, where you start by just looking at data and ending up with some type of answer. GitHub and Wikipedia, among other companies, are using Elasticsearch internally. So many people expect that it's an application, but it's not. As I said, it's an engine, so you can just download it, use it on your laptop across your cluster. And for the most part, all the capabilities that you see on this website or in this presentation are available to you as well, including in Spark. And to do that, you can use the Elasticsearch Hadoop project, led by yours truly, which is again available on GitHub. It's open source, Apache license, that handles the integration between the Hadoop ecosystem and the various components in it, and Elasticsearch. And among those components is also Apache Spark. So we integrate with traditional batch-based MapReduce and the libraries on top of it, such as Cascading, Pig, Hive, but also Spark. And we're glad to say that we have a partnership with Databricks, where we're also certified. We also work across multiple distributions. What you get with ES Hadoop is the ability to treat Elasticsearch as just another resource within the Hadoop ecosystem. So you don't really think about it as if that resource sits on HDFS. So you can write data to it, which means you can take any data, index it, and then you can read it back. Now, simply looking at this means you can treat Elasticsearch as a store, put data, get it back. But actually, the powerness of it comes from the fact that any data that you put in can be queried, can be analyzed. So it's not just a data lookup, but actually you get data insights. So let's see how this looks like. I mentioned the MapReduce integration. You can use that. It's pretty simple, right? We provide an input and output format. You can just plug that into with a bit of configuration, such as what are the resources that I'm accessing, in particular case index, whether I have a query or not, plug that into Spark context, and get the results back. Holden Carrao from Databricks had a presentation about that the summit last year. And again, this works, but that was last year. In the meantime, there's been a lot of progress. And while you can use the MapReduce integration, a bit biased I would advise against it because there are better options out there, such as the native integration that we have in 2.1, which is the current development branch, and we're going to get it out. What do I mean by native integration? Well, you don't have to pull in all the Hadoop intricacies. You don't have to think about writables and things like that, but rather use Elasticsearch directly from your Spark environment. So one way of doing that is on the slide. You have integration through the Scala API. So you can just import the org Elasticsearch Spark package, and you'll get two methods. Well, there are multiple methods, but the two essential methods that are available are the SRDD, Elasticsearch RDD on Spark context, which means, and again, on this slide, the code that matters is the one in bold. Everything else is just pure Spark. So I can take my Spark context and just run a query, and all that data from Elasticsearch will be streamed and made available to me as an RDD. In the same manner, I can take any RDD. I can have inside it Scala collections or case classes, doesn't matter. We can take any RDD whatsoever and index it to Elasticsearch. Notice that this is pretty much a one-liner. There are no serialization, there is no network connectivity, any of that stuff. All the infrastructure is handled for you. Now this is Scala, but we also have an API in Java. So in a similar vein, we have a dedicated package following the Spark convention, java.api, where you can have the ESRDD to run any query in Elasticsearch and get it back, and take any RDD that you have and just index it in Elasticsearch. Now, when you're doing reads, everything that we return is a pair IDD, so you can actually have the ID of the document, of the result, and its content. And also, we are making sure that the integration is native. So for example, if you're using the Scala API, your objects, your RDD is going to contain Scala collections. The same thing with Java. You're going to get the Java util collections. And internally, we don't convert it to Scala and then back to Java or vice versa. No, it directly moves, it's directly serialized because we want to be quite efficient in this. In the same vein, if your RDD contains a mixture of Scala and Java, whether it contains Java beans or case classes, we handle them all. So you don't have to do any transformation, unneeded transformation. We can just take the data and index it. We also have support for Spark SQL. I would go on a limb and say we're one of the first company, if not the first company, to support Spark SQL when it appears outside Databricks. So this means you can take Elasticsearch, point Spark at it, and connect to it through Spark SQL. So we support Spark 1.1, 1.1, 1.0, 1.1, 1.2, despite the fact that there's a minor breakage compatibility between the core and Spark SQL, and we now also support Spark SQL 1.3. That's available in master, and we're working hard trying to make sure that even though Spark SQL 1.3 is not backwards compatible with 1.2, within the code, we can somehow make things work. So even if you're using an older version of Spark, you can still use the same binary. You don't have to fiddle too much around it. Why do I mention this? Because on this slide, you'll see two trends, sort of, two code types. You'll see references, and also the way I speak, I'll be interchangeably talking about schema RDD, which in 1.3 are deprecated, but also about data frame. Internally, we do the detection, understand the environment, and give you the proper type. So again, you don't have to make the choices. They are obvious. We're infrastructure. We can handle that for you. So again, pretty straightforward. This is just Spark code. You just import the package, and in this case, on the SQL context, which is Spark SQL class, you can just apply the ESRDD. We're maybe thinking of changing that to DFRDD, data frame, or sorry, ESDF, Elasticsearch data frame. Run the query on an index, get the results back. You can simply run any SQL on top of it. It works transparently. In the same vein, we can save any schema RDD or data frame directly to Elasticsearch. And we're going to use the associated structure within the schema or the data frame to create the structure of the index in Elasticsearch directly. And we don't care where the data comes from. We're completely transparent. You can load the schema from a file. You can create it in memory, as I did in my previous examples, or you can just load it from a different system. We don't really care. We also support data sources. This is a feature that was added in Spark 1.2. It has two major benefits. One, you can do the entire declaration without writing any code, which is particularly important if you're from a Python environment. So rather than importing a package and saying, OK, use my classes, can we turn back, please? Now it seems to be too sensitive. I think there was a bit of a delay in my pressing there at the beginning. So as I was saying, now we moved way too back, and we move, OK, I have it. I'm full control here. Voila, OK. So on this slide, you can declare the source itself in a declarative fashion. Right? So you can say SQL load, and without importing the code, I can just point to my index and declare the data source. In this case, it's part of this package. So I don't have to import it in my code. I can just run it in SQL. Right? The snippet above, that's Spark 1.3. If you still want to use the Spark 1.2 style, we still support that. So rather than using SQL load, which was not available, you can just use plain SQL, which is create a temporary table, which is backed by this provider, in this case, Elasticsearch. Now, if you're using Scala or Java, again, there isn't any difference here is whether you prefer strings, which are more declarative, or you want to write code, potentially you're going to pick the latter. For Python, you don't really have a choice. But the next interesting and probably best behavior behind this is by being a data source, we fully understand what Spark is trying to do. So for example, we understand that when you're doing this SQL, OK, you want these columns, you are doing these operations. We implement the scan traits, which means rather than taking all the data and pushing it to Spark, so Spark can do the filter, we can push down these operations directly at the source and do it there. So obviously, it's going to be significantly more efficient in any regard. Now, as you've seen code-wise, and I hope you agree, things are pretty simple. It's the same Spark code. Nothing really changes. There are just some methods. And for the most part, you're interacting with the data source as it typically happens. But we also do some bit more work behind the scene. Elasticsearch and Spark are distributed systems. They scale out. So the more data you throw at it, if you want to keep performance up, you end up adding more and more machines. ES Spark connector takes that into account. So it's not just a client that connects to your cluster, but rather it actually bridges the two partitions from both systems. So as the systems scale out or scale up, so does your connectivity between them. This is what we call here partition to partition architecture. It means that for every call, for every one-liner that you saw there where you're interacting with the resource, whether you're writing or reading data, actually behind the scene, we peer any worker or every worker in Spark with its relevant peering partition on Elasticsearch, which would be a shard. So if you're looking at the data structure in Elasticsearch, any data there, any index has multiple partitions. The bigger it is, typically, the more partitions you're going to have. And for each partition, for each shard, you have for each index, you have replication, meaning how many copies of that particular index I want to have, right? So in case a node goes down, I don't lose that particular type of data because I have a copy somewhere else. And we take this into account. So for example, if you want to read data from Elasticsearch, let's assume that it's indexed. Again, in Elasticsearch, these settings are per index. So within the same cluster, you can have an index which potentially is small, only has 3 partitions, and one that has 10. One might have a replication of 3, another one a replication of 1. So it's entirely up to you how you manage your data, which means there is a lot of flexibility, and for the most part, the replication itself can be changed at runtime. So things are dynamic. That's why every single time, for every query, we look at the cluster state so we can figure out the parallelism there. So in this case, we have 3 nodes, and we have a shard, an index that has 3 shards, basically 3 partitions. And for each partition, also called a primary, that's a primary data source, you have also a replica, a copy of the data. So when you query this index, such as, find me something that matches this, we dynamically go with the cluster, figure out the number of shards, and for each shard, we're going to tell Spark that we require a peering task. And that worker is going to talk directly to its particular shard. So every query is actually parallelized, and each one working on its own subset of data in parallel. So the more nodes you have, the bigger your cluster grows, the higher the throughput between the 2 clusters. And this is a distributed system, so it's likely that things will go down. So in case the network goes down, for example, there is a small glitch or somebody just strips the wire, we actually detect that automatically. So we retry, we see that the node went down, and automatically fall back and reroute to the respective replica. So your job doesn't really feel it, except just that timeout that occurred, and then everything works as progresses, nothing happens. So you don't have to restart your job simply because one piece of data or one node just died. There was no state loss, and thus your job should continue as such. We also put quite a bit of effort into collocation. So Spark, for all intents and purposes, is fully aware of where this data resides. What are the nodes where the shards are located? What is their IP? And thus it can make the best matches to run the code as close to the data as possible. Typically, because of the flexibility between both Spark and Elasticsearch, the clusters can have overlays. So especially if you have beefy machines on the same hardware, you can run both Elasticsearch and Spark. And that's the ideal collocation, right? Because there's no network involved. But however, even if the nodes are somehow diverse or different, collocation helps a lot because we're talking here about network traffic that is just one hop. So it's really efficient rather than having multiple hops. One of the things that we're really excited is that in Spark is the ability of a quick reaction to data. As I've said, Elasticsearch is a real-time engine. So many of the things, many of the queries that you do get you direct results. And this has a natural affinity with Spark, which in many regards had the same low latency criteria underneath it. Now, there's been a lot of sessions, including the one right before me, on streaming. So because Elasticsearch is exposed through the connector as an RDD, you can use sparse streaming and take any input, any data input, and just save it or index it to Elasticsearch, among other things. And this creates an interesting model that we keep hearing about and that we humans tend to think about, which is this ability of reacting to data. The type of live loop where based on historical data, you build some type of model, and as the data comes in, you can react to it, either by inspecting it, but typically by looking at history. So you can make sort of informed guesses. You cannot just look at it, but actually based on history, figure out a certain pattern, certain heuristic there. And since I am specify model, wow, I'm already done on this screen, but on this one, I still see the next slide. So can we go back four slides, please? Yes, perfect. Let's stop here. I'll just look at the screen. Okay. Talking about live loop, one thing that we're quite excited about is the work done in the machine learning library, MLlib. And we're actually working, that's sort of part of the roadmap, of making things interesting there, as in creating a model in MLlib and pushing that information to Elasticsearch, but also creating the model by reusing the information in Elasticsearch. So if you take a look at the common use case, right, is fraud detection, which means classification. So as the data comes in, typically you want to react to it. Now, a traditional or basic approach is to say, okay, I want to look at the data and figure out whether something is off. So you do a query and say, okay, I'm looking at the operations, potentially specify a threshold, any cash transaction that is bigger than $1,000, okay? So you say, okay, I'm looking at the operations within the bank, I'm interested in the cash transactions and looking at things such as the owner and the location, okay? You get the data back and look at it. It works, but the more data you have, the more noise you have. So the least, it's more tricky to actually find the interesting thing there. You can improve that by using the analytics. So for example, in Elasticsearch, as I mentioned, we have aggregation, the ability of running a query, looking at the results, and doing something interesting with it, computing some type of analysis on it. One of them is significant terms, which as the name implies is in layman terms, and I'm aware I'm saying terms a lot, but that comes with the territory when you talk about a search engine, is saying, okay, I have a baseline and I run a query. So I'm looking at the results and trying to see what's different between the baseline and the results that I have here. Is there a certain infrequency or frequency, a difference in the term frequency? That is, do I have something that typically is ordinary, doesn't appear at all, it's like 0.5% of all my operations. But when I run a certain query, suddenly I see that it's 5% of my operation. So I see that within this context, this particular thing is significantly more important. Right, and you can do that right now in Elasticsearch. You can use the connector. I have the Spark context using the ESRDD, and I specify what you see there is a query DSL. It's basically a query to Elasticsearch where, say, I'm interested in transactions from a bank, in particular the transactions which are of type cash, and I create an aggregation. So as the data comes in, tell me what's significant about the field amount. And again, you can work on this. But you can also do something more interesting, more advanced. This is why we're currently in the POC phase, which is integrating, using a machine learning algorithm. So based on the data that you can already have, you can have a model that you can use to react to data. And this is, again, just Spark code, pretty much. This is an example of a clustering algorithm, k-means, that you've probably heard about at the various sessions that were even in this room, where what you do is take the data and you try to create these clusters. And once you have the clusters, you can see whether certain data matches that. Now, if you break it down, what you do is you have this hashing TF, which stands for hashing term frequency. So you can take the data, for example, in Elasticsearch, you can break it down by location, and you do what is called a featureize, which literally means I have this data I have to represent in one way or the other. Now that I have the featureize function, I can just pull into the k-means model, train, create the actual model, and then with the model, I can react to the data. So again, everything here is Spark code. This is the actual example for k-means. But the difference here is we're actually reacting to data and building a model in Elasticsearch. So we can create, as you see there at the bottom, a query, get the results back, such as the results that are pending, and filter them through the model. Is there something weird about them? And the nice thing here is this model is not unique. You can actually have multiple models, right? It's one thing to have 1,000 euro cash transaction in New York versus, say, in Eastern Europe, such as Romania. It's a slightly different thing. So the hashing function I've already mentioned, that's something that's already available in Elasticsearch. It's more just a hashing function. In Spark, you have a worker which has, for all intents and purposes, a limited set of memory. So it only has a certain view of the data around it. And thus, everything that it looks at, it's within that context of the window set. Now, in Elasticsearch, you don't have that problem because you can have all your data in Elasticsearch and still react to it right away. So your workers, even between jobs, can get the same information, not just between the scope data, you can have that if you want, but rather throughout the entire data, which means your model is going to be more accurate. What we have in the works is Vectorize API, which basically is exposing the internals within the search engine, such as a term vector, so you can see, okay, how many times these particular terms occur within this document, within this query? How many times documents occur within my query? What's the term position? What's the term score? What are its offset? This is low-level information that's already available across your entire data set. And it's about exposing that typically through a sparse matrix, so you can just plug it in and make it available in Spark and start using it right away. I think that's all the time that I have left. Well, a couple of more minutes so we can take some questions. Pretty much everything that you've seen here, code-wise, is fully available. You can get it on GitHub. It's documented, released. You can start using it. And if you have any questions, that's my Twitter handle. A GitHub address, you can find all this code and the website for documentations. First of all, thank you. And if you have any questions, I have 3 minutes to do my best to answer
We have
them.
more than 3 minutes, actually.
Wow, more
Let's
than
thank
3
Costin.
minutes.
Please bring any questions you have to the one of the 2 microphones.
So with data in HDFS for Elasticsearch, does it still do all the replication and stuff, or does it let HDFS handle it?
So that's actually, you asked 2 questions.
Okay.
You said, with the data in HDFS,
Yep.
does it do replication? So you can point Elasticsearch and say, as a storage, the backend storage for Elasticsearch, you can use HDFS. And you can do that. You can take HDFS, you can expose it for NFS, it becomes a local partition, point to it. However, you don't really want to do that for several reasons. HDFS, it's an archiving store for many purposes. It's not a real file system. So things like fsync or last file on close have different semantics. Second, its main intent is to store data. So random access, for example, is quite slow. You can add caching on top, but that's like patching. I'm not saying it cannot be done. Rather that Elasticsearch is great, but it's not magic. So if you put it on top of a slow store, its real-time capabilities are basically going to divert. Now, if you want to do that, that's fine. And even there, you can disable replication. So Elasticsearch internally has replication built in. If you say, hey, I don't want to use that, that's fine. There you go.
Thanks.
Do you have support for querying nested documents through Spark SQL?
Yes. So nested documents, for all intents and purposes, are basically just documents. You have to be aware of them when you typically make the query. So within the actual SQL that you make, typically we refer directly to the target. So you can even use, for example, the fields directly. So within your table definition, you can say, I'm only interested in these things. And your index doesn't necessarily have, your table definition doesn't have to map the entire index. You can just say, I'm interested in these particular columns, and the rest of the index, especially if it's a large one, it doesn't really matter. So you have a lot of flexibility in how you get the data. Or what we're interested from the connector's perspective is to understand, to create sort of the query. And again, nested document is just another document there, except that it has this special capability. So long answer short, yes.
Thank you.
So this connector handles async type of you return a Scala future?
So not right now. Your question, I guess, yeah, I don't have to repeat it. So this is so the data is being returned async, right? If you look at it, we don't, when you do a query, we don't just go there, get the results right away. Actually, we're streaming the results. So what we're doing, right, this is iterative or streaming-based operation where you'd run a query, we do it, we know what the results are, but we load them lazily. So when you start iterating through the RDD, we take a chunk of it, which is fully configurable of the data, put it here, typically like 50 documents, look at it. You want more, we go get more. So the operation internally has to be async. Now, whether you want to put from the API's perspective a feature on top of it or not, that's entirely up to you. Considering that everything in Spark is lazily, is basically right, functional programming, everything happens when you actually need it, there is really no point in doing that. Every RDD that you set, right, just like in Spark, unless you're going to do any operations on it, we're not going to actually make an operation to Elasticsearch. That will only happen when you actually have to work on the data. So from this perspective, you can keep changing them. It's entirely up to you how you want to do it. Yes?
Quick question. When will the code for exposing Lucene term vectors be available?
Yeah, so that's something in the works. We need something also from Elasticsearch. So that information is available. We want to expose it as an API. So okay. The connector is potential consumer of them, but somebody else might want to look at it. I believe there is an open issue already, Elasticsearch, the project. And once that's out, give or take, I'm on the record here, so I don't be too optimistic. I guess it would be between, the work probably will get started on 3 weeks. Oh. We've all been at the conference in Elasticon and going back, so everybody's a bit traveling from development-wise. But I would expect really to have something in the open as code-wise, something that you can use 1 month from now, again, give or take.
Wonderful. And then the second thing is, does the API handle dynamic mapping as well, or do you have to predefine your schema?
The API for what exactly?
Oh, I'm sorry, for writing to...
Yeah, so it's entirely up to you. The semantics of Elasticsearch themselves do not change. So for example, if there is no index, when you push the data, okay, we take it, we infer the schema and create it. And as the data moves on, right, that's the schema list, yes. You can migrate it. If you go in production, there are cases where people want to have full control over it. So then you can create the mapping yourself, log the index, that's entirely on the Elasticsearch side. So as the data comes through, if there is no index or potentially one of the documents that you put in, it's incorrect, doesn't match the schema, it gets rejected. Also notice that one thing that we do is if there is a fallback, for example, if the cluster is very busy, we actually retry. So we push the data, Elasticsearch is going to index, let's say, 20% of the documents, and then we'll retry the rest of the 80 documents. So this is typically useful because if you log down the index, you end up with a very sort of streamlined pipeline of data going to Elasticsearch and back.
Thanks. Thank you.
All right. Thanks very much. Let's thank our speaker one more time.